Now, I've been sitting on this present that a student gave to me over 10 years ago when I was working in Taiwan. This student's actually doing a PhD in brain surgery in America right now. So thank you for this little toy. The good thing about doing videos is you end up doing background research and analyzing things that you would not normally do. And so what I normally do is just use this for junior science and just explain that the gas, the gas laws, so the gas is getting colder and it's shrinking. And so what you can see here is you sort of have the head going into the liquid, and then the water evaporates, and that causes cooling of a couple of degrees. I think they say up to 5 degrees. And that I would normally say that the gas cools, and so it shrinks, and that pulls the liquid up, and then it unbalances, and so it gets heavier at the top, and then it sinks down. And when it sinks down, it refreshes the liquid to keep evaporating for the whole day, basically. And then at the bottom, the tube is exposed, so all the gases and liquids and temperatures recalibrate. But when you sort of look into it, you sort of realize. I'm just going to try and give a proper explanation. So the substance itself is dichloromethane, so proper name, UPAC name, 1,1-dichloromethane, and its boiling point's only at about 40 degrees. And so they use that chemical, especially rather than water, because it has a very much more fluctuating vapor pressure. And so the question is, well, why is that? So that the question is this change in gas caused by the cooling of the gas or the condensing of the gas? And so I asked, so I had to query ChatGPT to do the calculations for me to save me some time. Thank you. And just looking over them, they seem to be fine. So I just double check this data here. So just going to Wikipedia, it does seem that the temperature differences are about correct. If we're looking at 10 to 40, there is that sort of curve going on. And so those numbers look legit. This is probably for senior chem. So senior chem, we know the ideal gas laws. We can leave it in ATMs, although we should really be putting it in pascals to use the correct units. And they've converted. You must convert to the Kelvin, otherwise the numbers will be out. And so there's only a 1.7% drop due to the cooling, which is quite small. And then if you look at the condensing gas using those tables, it's the pressure drop we can just look at directly. It's in a different unit, but we're just using percentages. So converting it to a percent, that's 12%, so it's 10 times greater. So this now fully explains that the change in pressure is definitely mainly due to the gas condensing into a liquid, and very little to do with the gas actually becoming colder and shrinking. And if you look on the internet, there's so many videos with tens of millions of views, and they either give no explanation or the wrong explanation, or the really good ones actually do know. The engineers know that it's the condensing gas, but they don't explain why it can't be the wrong explanation, which is quite common as well. All right, so I hope you enjoyed that.